Thank you very much for the opportunity to speak here. So my talk today is based on some work in progress, and part of it was posted as a preprint. And I want to talk about something that was mentioned in many talks, but hasn't really been discussed much. That is a property of reflection positivity. So one of the central themes of this workshop is Kitai's conjecture that says that if we consider some classifying spaces of invertible phases of matter, like in dimension D, which we can think of as like space of parameters of all possible systems in this phase, that these spaces are organized into a loop spectrum in a sense of homotopy theory. And Kitai gave some convincing argument that this is indeed the case, but this argument is rather formal, so it kind of doesn't really use much about the systems that we consider. And the real problem is to actually compute the spectrum, so compute the homotopy groups. And at the moment, we don't really know much about these homotopy groups. So the kind of situation is was summarized by Alexei in his last lecture last week. So we understand very well free fermionic classification, but we don't understand the classification of invertible phases. And when I'm saying that we don't understand, it's not that like we don't have like some concrete model for them and some like theorems about it, but I'm saying that even about ideas to how to classify them. So we need some new methods to understand it.
So here the D is a spatial dimension?
Yes, it's a spatial dimension. So I would say even some physicists might not be even convinced that we know the answer. So we understand pretty well classification and dimension for one-dimensional systems, but already in 2 dimensions, we only have some conjecture. So we have some states that we can kind of construct explicitly. In the Fermionic case, is this P plus IP superconductor state, which is a state of free fermions. In the bosonic case, is this A state, which I believe to be non-trivial. And the question is how to prove this mathematically. So we only have some kind of argument that this is the case. And it is kind of conjecture that this is probably all that we have, but we don't know. And in high dimensions, we only have like some prediction from kind of TQFT approach. Quantum field theory was, of course, successful in many problems in nature. So maybe at the end, it's going to give the right results, but we don't understand how to relate this field theory to lattice systems.
What about 16Z?
Yeah, so this 16 is something that Alexei mentioned in his last lecture. So there is some, so this numbers that we're supposed to be associated to invertible phases for bosonic and fermionic systems, and it is believed that these numbers, they differ by multiple of 16. Yes? Yeah, so this is like the first non-trivial homotopy group of the spectrum that corresponds to a Berry phase, Berry classes. In this sort of invariance, if we consider a system with some additional symmetry, the Z kind of produces this homology classification for SPT phases.
And also for this, for the 16Z, will the generator have a framing anomaly or not here? It's related to.
Well, I'm talking just about some concrete states here. This 8 state and P plus IP. Whether it's 16, we actually don't know. So it's just conjecture.
The E8 state is supposed to have a framing anomaly. Then maybe there's a triple E8 don't have framing anomaly. Whether that relates to how the source is quantized.
Okay, I guess I'll mention something about it at the end of the talk. And today I'm going to concentrate only on 2-dimensional systems because this is kind of the first non-trivial case that we don't understand. So in this topological quantum field theory approach, the main assumptions, which are the strong assumptions, is that we consider systems which have symmetries of Euclidean space and reflection positivity. That you can roughly say that this kind of unitarity in space. But when we consider some general quantum many-body systems, we do not have these properties. Well, first of all, the systems don't even have like in general discrete translation invariants because there might be some disorder. But moreover, we don't have this property of kind of unitarity in space if we just consider some arbitrary Hamiltonian. So not like only very small subset of all the systems, you can say that it's kind of relativistically invariant in all directions. Well, you can perform this weak rotation.
When you say unitarity in space, do you mean some reflection symmetry?
Yes, and I'll explain in detail what it is. So some basic questions that we can ask about this quantum unibody systems is, what happens if we just slightly shift the system? Let's say, well, if we apply some isometries of Euclidean space, whether it's like in the same phase, whether like we can always find some. So maybe reflection positivity doesn't hold for any state, but maybe we can always find a representative in a given phase for which this reflection positivity holds. And even the most basic question, so physically it is natural, so if you consider some invertible state and just take its complex conjugate, then this complex conjugate is supposed to be an inverse of this phase. So that if we stack these two systems, that's supposed to be a trivial phase. And even this statement is has not been shown that this is actually the case. So, and in order to try to answer this question, we need some setting where we can work with, so somehow formalize what we mean by invertible phases. So, and I'm going to consider a setting of quantum statistical mechanics working directly in the thermodynamic limit. So again, like essential things that I'm going to say, it doesn't matter like what exact setting I'm considering, but just for concreteness, I'll give some definition. So, so we consider some lattice in the Euclidean space and some finite dimensional Hilberts associated with sides of this lattice, and we consider sister algebra of observables associated with this Hilbert spaces, and systems would correspond to some states on the sister algebra, which are just normalized linear functionals, which are positive. So positivity will play an important role today.
The VJ is finite dimensional.
Yes, well, for concreteness, let's consider finite dimensional, but yeah, I can also relax this condition. And what I'm going to consider is, so I want to introduce some equivalence relation on such states and some monoidal structure that induces a abelian group structure on this equivalence classes. So this monoidal structure, of course, has a very simple physical meaning. So we can just consider a stack of two systems. And we can consider the unit for this monoidal structure as a trivial state. That is just a product state of pure states on each finite dimensional Hilbert space. And we'll introduce equivalence relations on the states using two basic equivalences. So first of all, we want to allow to kind of stack arbitrary trivial state with any given state psi. So we'll say that they're equivalent if they're related by this operation. And you want to impose automorphic equivalence, saying that two states are equivalent if there is a certain local automorphism relating them. So if you can precompose this automorphism with a state, we get another state. And of course, I need to specify what local means. So, and we'll say that the state is invertible if there exists another state such that the stack is in a trivial phase. So we have this equivalence relation and some multiplication with inverses. So I need to specify this locality of the automorphisms, and I'll choose a very kind of weak notion of locality. This locality is defined in the following way. So I'll consider my two-dimensional plane, and I consider some cover of this two-dimensional plane by cones. So this picture, so I have cones AI, which correspond, so I just choose some point on this plane and just consider rays coming out of the origin. So this is kind of the first layer of cones, and then there is another layer of cones B, which cover this rays separating cones A. And I consider automorphisms which are localized strictly inside these cones. And I'll say that an automorphism is associated with this cover if I can represent it as a product of this automorphisms localized inside the cone time some inner automorphism of the algebra. So it's some like local conjugation with the unit tree. So
right, localized within which cones? The colored ones or the white ones?
So there are cones A which are bounded by these gray lines, and there are cones B which are bounded by these orange lines. So the thing is, like, if you think of this like the base of this cones at a circle at infinity, then this kind of product looks like a quantum circuit. So this definition might look abstract, but so the reason why I impose it is because it's kind of the weakest that I know for which things work. And all this like usual definition that we usually consider, like adiabatic evolution of two states, this produce automorphisms which are of this class. So we can always represent them in this product. And it also kind of allows to work with all these automorphisms which have tails. So somehow it automatically included in this. And this notion of locality was actually introduced by Peter Nikins in his lectures. Like he gave kind of very similar definition of equivalence states. Yes?
You want to at the center?
So at the center, I have some inner automorphism of this algebra, this alpha C. So this is just conjugation with some local observable. So, and I'll say that these two states of this sister algebra are equivalent if for any conical cover of the circle, whatever fine this cover is, I can find some automorphism associated with it that relate these two states. So it turns out that this equivalence relation is rather flexible. So it allows us to relate states which are obtained by some simple rotations of this sister algebra. And this can be done like using this kind of Eilenberg-Swindle tricks, kind of in the spirit of the proof of this Kitai's conjecture about loop spectrum. So it's kind of using this folding operations, one can relate this state like rotated states. And also if we kind of perform just a usual reflection, then it produces an inverse state. So if we just stack the state with reflected copies, then we can apply some automorphism and get the trivial state. But questions which are not trivial is whether we can always find a representative which is a reflection positive, and whether if we complex conjugate the state, then it produces an inverse state, inverse phase. And now I have to explain what reflection positivity is. So this reflection positivity is something that was actually discovered here at Harvard University more than 50 years ago by Osterwalder and Schroeder. And the original goal was to kind of find some condition on Euclidean field theory, on some probability distribution in a statistical model, which guarantees that we can perform a weak rotation and kind of treat the spatial direction as time. And one necessary condition for this is that, so since kind of time reversal in quantum mechanics corresponds to complex conjugation, one condition is that if we consider some observables living, let's say, in the upper half plane, and we perform a reflection, then the expectation value of this observable should be complex conjugated of expectation value of original observable. That's like a reflection part of this reflection positivity. But positivity is a stronger condition. That actually, if we consider average of the product of these two things, then it is always positive. And one can think of it as that if one tries to associate like a vector space of states, if one tries to cut the system along this reflection plane and associate some vector space, then this vector space has a positive definite inner product, so that we can talk about Hilbert spaces. That's kind of a Euclidean picture, but now how to formulate this reflection positivity in quantum mechanics. So for that, let's consider like a simplest case. Like let's say we consider just quantum mechanics, like zero-dimensional system. So and we have some finite dimensional Hilbert space H, and we have algebra which is just operators on this Hilbert space. And I want to consider like a double system. So I take the system and its copy, and I want to think of this copy as a reflected system. So I introduce this condition on vectors in this double Hilbert space. So I consider some anti-unitary operator J, which just permutes and complex conjugates vectors in this Hilbert space. And I'll say that vector is reflection positive, it is invariant under this J, and I have this condition for any A that acts on the first copy.
So H star for you is the pool or the complex conjugate?
So here, I assume I have some identification between H. Yeah. Now, this reflection positivity is closely related to operation of purification of a state. So suppose I have some mixed state on my original system, and I can find a pure state on this double system such that its restriction to my original system produces a state. So I can find a vector, some omega, such that I have this property. But in general, there are like many purifications of a given mixed state. There is, however, a unique purification if we require this condition of reflection positivity with respect to this anti-unitary operator J. And this one we will call canonical purification. So the nice thing about these reflection positive vectors is that they form a positive cone inside this Hilbert space. So I can take a positive linear combination of these vectors and they're still going to be reflection positive. And the interior of this cone, that corresponds to some vectors that I call strictly reflection positive. So it's important that these vectors have a non-negative overlap with all these vectors inside this cone. So in this condition of strict reflection positivity is something that, like in the case of, so when you consider like star operations in star algebras, you can think of it as this positivity in time. And this condition kind of similar to faithfulness condition on states in C-star algebra. Now we can consider even like more generally some mixed states on this double system and kind of define in the same way reflection positivity condition. So this anti-unitary J defines some anti-linear automorphism of my algebra. And the nice thing about this reflection positivity is it's kind of stronger than this condition of reflection symmetry. So it kind of automatically implies that if my state is reflection positive, then it is invariant under the CRT symmetry. So that was just for quantum mechanics, but we really want to work with many-body systems. And many-body systems are described by some C-star algebras. So I need some generalization of this reflection positivity condition and canonical purification for C-star algebras. And that was done a long time ago. So if we just consider some arbitrary unital C-star algebra, we can consider its opposite algebra, which has opposite multiplication. And we have some canonical anti-isomorphism induced from the star involution on the algebra. And we can consider this canonical anti-linear involution that just, again, permutes observables and then complex conjugates them. And define a notion of reflection positivity for states on the tensor product of my algebra and its opposite. So now if I consider some...
Could you go back to
yes.
The lattice and state on a tilde? Okay.
Yes. Okay. So it's so introduce reflection positivity and strict reflection positivity like in the previously. So now if you want to consider this canonical purification, it is not defined for any state, or at least it would not produce like a pure state, this algebra, but there are some conditions that we can impose on a state that for which this canonical purification produces a unique pure state on this doubled algebra. And these are conditions which are, so the condition of that the state is factorial. So basically what it means is that like for this algebras that I'm considering, like which are uniformly hyperfinite, that means that I have some decay of correlations at infinity. And if the state is factorial and it satisfies this condition of reflection positivity and some condition relating how these algebras are embedded into representation associated with the state, then there are theorems by Varanovitz which are like statements from basically, well, which were proven even like before Tomito Takisaki theory, that there is a unique purification of any factorial state on the C-star algebra.
Sorry, where's pi psi? Is that like a GNS representation?
Yes, it is GNS representation associated with state psi. Moreover, it tells us when these pure states that we get in the purification, when they're equivalent to each other, when this representation associated with the states are unitarily equivalent. And this condition that kind of equivalent to this unitary equivalence of purifications corresponds to quasi-equivalence of states on my original algebra. So again, this like quasi-equivalence can be kind of defined in this apparently algebraic language, but roughly physically it means that the states coincide at infinity. So if I consider observables outside of large balls, then the evaluation of the states on this observables, they would be very close to each other. So for any epsilon, I can find large enough ball where the thing holds.
Quick question.
Yes.
J positivity, where is there's no statement about the the state there, are you using like the J from like Tomita-Takasaki theory? What are you doing?
No, here it's all in the language of C-star algebra.
Sure, but whereas so J positive, you said J of this is greater than or equal to 0.
Yeah,
There's no statement about omega in that.
So J is defined here.
Yes, I understand that.
Yeah.
So, but you say a state is J positive if this condition holds, but the condition does not say anything about omega.
I'm so sorry. Yeah, what I mean here, yes, it's omega, not J. Sorry,
Okay.
that's a typo. Yeah.
Would I?
Okay, so and it is indeed related to the Tomita-Takasaki theory that you mentioned. Basically, this if you consider like representations, GNS representations of this algebra associated with this state, then this automorphism it is implemented by some anti-unitary operator. And this anti-unitary operator coincides with this Tomita's modular conjugation. But it's not going to be important for what I'm going to say in the following. So yeah, the only thing I probably mentioned that this cone of reflection positive states. So there is an analog of this cone that we had in the finite dimensional case in this infinite dimensional setting. So all these vectors in this Hilbert space, reflection positive vectors, they span some positive cone. Now, question that we want to ask is, so suppose we have now many-body system. So we have some invertible state. And this canonical purification produces a natural recipe. Well, it gives a recipe to produce this reflection positive states. So what we have to do is we just have to consider restriction of the state to a half plane and then canonically purify it. And it's going to be unique reflection positive state that has this coincides with our original state in this lower half plane. But the non-trivial question that we have here is whether this operation preserves locality. Because remember, we start with some invertible phase, and we want this, when we form this operation, that this new state is still going to be invertible, so that we have like the decay of correlations. So the reflection positivity from this perspective is not something like, it's not an assumption, it's something that we need to check in many body systems. And so that's basically the question that we are asking. And this question is rather non-trivial because of the following issue. So there is some interesting counterexample. Alexei told me about it. So if we consider a state that so we can consider like a one-dimensional state embedded into a two-dimensional plane that look like this. So we consider like a chain. So we start with some trivial state, which is just the ground state of this on-site Hamiltonian, and then we apply certain unitary operator, which is like a quantum circuit, and then we produce a ground state of a model known as cluster state. But then suppose we take this cluster state and consider its restriction to odd spins or even spins, and then perform this canonical purification. Then resulting state is going to look like this. So it's going to be a linear superposition of two states, which are just collection of EPR pairs, but of different kinds. So one is like EPR pairs 0, 0, 1, 1, and another one is 1, 0, 0, 1. So the states, so the state looks like this JG state. So it has some long-range correlations. So if we just start with some arbitrary short-range entangled state and perform this purification, then we may not have short-range correlation. And that causes a subtlety with this procedure of canonical purification. However, if we consider a thermodynamic limit first, and then perform purification, then the subtlety actually disappears. And the reason why is because, so if you consider this mixed state that we have on our odd spins, and first take thermodynamic limit, then the state is going to be maximally mixed state. So there is some kind of non-commutativity in the procedure of this canonical purification and taking thermodynamic limit. But because of this theorem that I mentioned earlier, this problem actually absent in thermodynamic limit. So, and the general statement is the following. So suppose we consider some one-dimensional state, which is produced by three automorphisms. So one automorphism is localized on the left half chain, another one is on the right, and then we apply some inner automorphism somewhere well, conjugation by some local observable. So the states satisfy this the split property. So they have some kind of finite entanglement between left and right half chains, roughly. And now, if we consider such states, and then we restrict the states to, let's say, even spins, and perform this purification, then this theorem of Voronovich that I mentioned about quasi-equivalence of this, well, equivalence and quasi-equivalence of states and their purifications implies that this purified state is still going to satisfy split property. So it's something that allows us to prove that this problem do not really appear.
Could you remind us what is quasi-equivalent?
So quasi-equivalent is basically that these two states are equivalent at infinity. So like if for any epsilon I can find like some ball such that for any observable outside of this ball, this averages are less than epsilon, if observables are of norm less than 1. So the point is that this kind of theorem allows us to prove some version of locality of this canonical purification. So it's not, so this split property doesn't hold for any state. So like, for example, if states are gapless, it's not true. But for states of this which are gapped or short-range entangled, this property holds. Yes?
Somehow, what you just explained about the quasi-equivalence, it resembles a little bit what we've heard this morning by Alexander Schenkel about the Doppler-Haag-Roberts condition. Though it was not outside a ball, it was outside cones, that representations, or I mean here there are states, but they're equivalent via GNS to representations are equivalent. Is that related? Super selection condition?
Well, well, I guess you're talking about split property in general many-body systems, like in high dimension. Yeah, and actually, like on the next slide, I'll.
Okay,
well, they look like, well, maybe it's a little bit related to it, but yeah, I'm not sure it will fully address your question. So now the thing is that now we can use this fact to prove what we want for 2D invertible cases, and the reason is the following. So suppose we start with some invertible state. So we take its lower half, like restriction to lower half plane, and then canonically purified. So we want to prove that it's still invertible. Well, the state looks the same in this lower half plane, and it's going to be just a complex conjugated state in this upper half plane. So I can apply the same kind of automorphism localized inside these cones to disentangle my state everywhere, like outside of this reflected half plane. So if I apply some automorphism, my state will look like this. So I can get rid of all this entanglement inside this half plane. But what I get is some state that's going to be effectively like one-dimensional. It's going to be localized inside these cones. And I will have the split property for the states because the state, well, if my original state is in a trivial phase, then the state are produced by exactly by the 3 automorphisms that I mentioned. So if I now if I start with any state like this and perform canonical purification, I will still have the split property. So basically it proves that with the definition that I gave, where if I perform canonical purification, then I get an invertible, invertible state. Now you can ask, what if I impose, so I impose some rather weak notion of locality with these cones. What if I impose some stronger locality? What if, for example, I impose like equivalence of states with some quantum circuit with like finite range in the bulk, not like on this circle at infinity? Well, it turns out that, though I'm not going to explain it today, because it's kind of technical, that basically this kind of definition that I gave, you can always find, like, using some manipulations and tricks, these folding tricks, you can always kind of decrease correlations. And you can always, like, produce some state for which correlations, which can be produced by something, like, relatively local. Yes?
This slide you just explained is in 2D, but then you said it follows that any invertible phase. Do you mean any 2D invertible phase? Or
Only 2D. So today I'm only talking about 2D. So this argument actually doesn't work in high dimensions. So this is a general statement that, like, whatever kind of definition of this you want to work with, like of this adiabatic equivalence, it may not be true that this canonical purification produces states with which are inside this class of state that you consider. But what is true is that you can always find a representative for which this is true. And that's like kind of what one would mean by kind of reflection positivity for this invertible phases. Okay, so we have this now nice properties. So I mentioned that we can find this reflection positive representative. And actually, if we have this reflection positive representative, and also we know that this reflected state produces an inverse, we can show that a complex conjugate state also produces an inverse. So now we understand this kind of very basic properties. And now we want to ask, can we construct invariants of the states and classify them? So, and as I said, like physicists believe that there's supposed to be some z-valued invariant associated with this invertible phases, which they call chiral central charge. And this non-trivial generator of this invertible phases, like in the bosonic case, corresponds to this 8th phase. So why do people believe that this is the case? So the first argument comes from the fact that under some favorable circumstances, if you consider like this material, that sometimes edge modes can be described by conformal field theory. And in conformal field theory, we have some big symmetry group, the chiral versor symmetry, that is central extension of the group of diffeomorphism of a circle. And the central extension is called this chiral central charge. And for holomorphic CFTs, which kind of correspond to an invertible version of vertex CFTs or vertex separated algebras, the chiral central charge is quantized for bosonic systems and fermionic systems. Another argument comes from this kind of conjecture from TQFT, this Kapustin and Fritz-Hopkins conjecture. This invariant Z is supposed to be related to signature of 4 manifolds. And this factor of 16 kind of appears in this in the world of 4 manifold as kind of the fact that spin manifolds have a signature divisible by 16. But of course, like in general, like if we study many body systems, we do not have all the symmetries and kind of relation to TQFT, so we don't know how to prove it. So we need some additional argument to so even if we believe that the C minus is well defined, we need some argument that actually we can formalize mathematically. So another argument, physical argument, comes from the following effect. So even though we don't have any diffeomorphism symmetry on the lattice, we still have conservation of energy. And at very small temperatures, CFT predicts that there is a flow of energy proportional to this chiral central charge. So since this kind of, well, now if we kind of deform our system out, like from breaking this Virasoro symmetry, since we still have conservation of energy, one might expect maybe this current is still robust. And even though kind of we don't know how to derive this kind of formula, this current will be the same, like for a given phase. And Kitaev tried to kind of formalize this argument in kind of lattice system, but still we don't know how to kind of formalize it mathematically. And there are like some technical subtleties related to the fact that we don't understand how this. So if we kind of, well, the thing is like this formula corresponds to some states which are very close to the ground state, but at some finite temperature. And we don't really understand how kind of locality properties of the states, well, we don't really have a good control over these properties. But anyway, so even if we have like, can formalize it, so recently it was also, there was some conjecture about how to extract this chiral central charge from bulk wave function, so we don't know how to prove it, but also even if we kind of somehow manage to prove it, it doesn't answer the question why this chiral central charge is quantized for invertible phases. And in high dimensions, it's even more complicated because in high dimensions, we're supposed to, like from this conjecture, like relation to TQFT, we're supposed to have a bigger symmetry group, like while this kind of energy relation, it's only kind of corresponding to SO2 that kind of mixes one spatial direction and time. So that's why I'm going to describe another approach today. So if you consider just the one system, then it might not have any manifest symmetries. But if you consider a stack of n systems, then they always have a symmetry. And the symmetry is just a permutation group. So it acts in a way that just permuting sides. And if permutes the whole copies, that's a symmetry of a state. So we want to use this symmetry. And what may happen is that even though it kind of acts in a very simple way, the symmetry might have a non-trivial trivialization. And in order to study how the symmetry acts on lattice system, we want to analyze defects for the symmetry. So we can choose some like Z-mod-n subgroup for the symmetry and produce a state. So if you have n copies of material, we can, so I'll first explain kind of physical idea and then I'll explain how to formalize it mathematically. So we can consider a state that looks like on this picture. So what we do, we take this n copies and we consider some branch cut, let's say along positive real axis, and then we so we cut all these materials and then we glue them such that if we go around this origin, then all these copies are permuted. So we have like a n-branched cover of a plane this way. And I'll call such defects twist defects. And such defects we of course studied in conformal field theory. In conformal field theory, we know that such defects have a non-trivial statistics. So if you try to permute such defects, then they have like a non-trivial spin associated with this permutation. And since statistics is something that is manifestly, so it's not really relies on kind of symmetries of a space. So it's something very robust. One may expect that even if you consider like lattice systems where we don't have any symmetries, the statistics still gonna be the same. So that's kind of basic idea. But there is a subtlety. So subtlety is that you want to produce this twist defects in some non-ambiguous way, so that this kind of topological phase is well defined. And far away from the origin, there is kind of canonical way how you glue these materials, because we just permute them. But near the origin, we need to somehow kind of glue them. So we can always have this freedom of adding some additional qubits and kind of entangling them near this origin. And well, there are some subtleties which kind of do not matter, but the subtlety that matters is that we can stack them with some qubits which have non-trivial charge under the Z-mod-n symmetry. And this charge actually affects the spin of topological league. So question is there some canonical way of fixing this charge? And that's where reflection positivity helps. So how it helps? Well, suppose we have this kind of twist defect. And what we can do, we can produce a state that has, so we can then perform this kind of transformation in the complex plane, like taking one over like this map, and produce a state which is invariant under rotations, under Z-mod-n rotations. And this ambiguity, this charge ambiguity corresponds to this angular momentum ambiguity at the origin. Now, a statement is that there is only, well, if we consider states like this, then there can be only one reflection positive state satisfying this property. And the reason why this is the case, as I explained, is all these reflection positive states, they sit inside this positive cone. So if I consider some states which have strict reflection positivity, then it cannot be orthogonal to any state lying inside this cone. So somehow reflection positivity chooses some particular angular momentum for all the states. And having such a reflection positive representative, we can always then like perform inverse transformation and produce this twist defect. Okay, so now once we have this twist defects, what we can do, we can.
What could be a linear combination of states with the angular momentum? So
Well, it's not going to lie inside this cone.
okay, so you say only states with specific angular momentum.
Yes.
Is there a distinguished angular momentum?
Yes. So, and if you consider, let's say, one-dimensional spin chain, like let's say we don't consider this infinite system, we can consider just a system on a circle. And then can consider like some Hamilton, well, some states which are invariant under rotation and reflection positive. Then the statement is that this angular momentum, we have canonical angular momentum, and this angular momentum is going to be 0 for reflection positive states.
But in general, the specific angular momentum could be done.
Yes, of course. I mean, you can have states which have non-angular momentum, and actually, even if we just impose CRT symmetry without positivity, then there are still such states. But positivity somehow is a strong constraint.
If I only cared about conformal field theory, then I already knew what the twisted sector was.
Yes.
And so then presumably that's the same one that you're telling.
Yeah, but but we need something like that fixes this angular momentum without resourcing. So now, once we have the states, we can study what happens if we permute them, and kind of there is some procedure that kind of allows to extract this kind of universal phase by moving this kind of twist defects in the appropriate way so that this all this kind of non-topological phase cancels. And the statement is that these numbers that we get when we switch these defects, that it is a topological invariant of this original state that we started with. Okay, so that's kind of a physical picture. Now let me try to be more precise and say how to formalize it mathematically. So now, so we start with a state on n standard product of my original algebra. And now what I want to do, I want to split my plane into three regions, like A0, A1, and A2. And then I want to see what happens if I just, so I have this permutation symmetry automorphism of the algebra, and I want to see what happens if I apply this automorphism just to region A0. So like deep inside this region A0 is going to be kind of the same state, but the state is going to be different near the boundary of this A0. So in this infinite volume setting, if I just apply this automorphism, then I produce a state that that is not unitarily equivalent to my original state. So it has a different behavior at infinity. However, what I can do, I can choose some cones which cover this race, as cones B, and I can find some automorphisms, Z mod n invariant automorphisms, which kind of which change my state near this boundary and return it back to my original state. So and if I just choose one cone and one automorphism inside this cone, then I can just undo this kind of permutation everywhere along this along this ray. So I can by applying this kind of combination of this automorphism W and kappa, I produce a state that is precisely this kind of twist defect. So I kind of perform this permutation only along this ray. And now I can choose this automorphism for different cones for another race, and I can produce some automorphism that actually preserves my unitary equivalence class of my state psi.
These are still pure states? Or?
So states are all pure, yes. And I just study automorphisms.
Even the symmetrized.
Yeah, so it's just a tensor product of pure states, so it's still pure. The state psi.
Patients on one state. Usually we'll have to use a sum to obtain the symmetric state under the action.
Oh, I just apply automorphism to a pure state, and it's still going to be pure.
Yeah, and you apply many of them.
Yeah.
In a random order or?
No. So I just concrete automorphism. So, for example, on this picture, I just apply this composition of W and kappa. And on the next slide, I choose another kappa and apply this product of all these automorphisms to produce new automorphisms that I call W0 tilde. But the important point is this new automorphism, it preserves unitary equivalence class of my state psi. And kind of physically, I can interpret them as something that kind of moves this twist defects along this path formed by this gray rays. But since it preserves unitary equivalence class of my state, I can associate some unitary operators with them in the GNS Hilbert space. And because I know that this automorphisms commute, that kind of follows because I choose all these kappas in a way, in a Z-mod invariant way. I know that these unitaries commute up to some phase theta. And that's going to be this invariant that I was talking about.
This is not the trivial invariant?
Sorry?
Give us examples of values of this invariant?
Yeah. So, sorry, just this P plus IP superconductor is something where we can compute this, and it's not trivial.
It's not just like a third root of Hübner's.
No. It's going to be the same expression as in CFT. So, this one.
Shows up?
No, not really. Okay, so yes.
So, where did the canonical purification construction enter here?
So it enters in like fixing this angular momentum ambiguity that I was talking about here. So yeah, we need to produce some state which has this reflection positivity and Zeemoten rotational invariance that kind of produce like fixes this canonical twist defect.
So there's also like a reflection plane.
So for the Zeemoten invariant states, we just have to require this reflection positivity for just one plane, because then it is automatically holds for rotations of this plane. So in some sense, you can say this like this: you know how to study rotations by just knowing how to like study reflection. So if you know how states behave under reflection, then you know how they behave under rotation. That's basically why reflection positivity kind of fixes. Okay, so now, so these are just some U1 phases. Now I want to understand if these phases are quantized. So we know that this chiral central charge is supposed to have some quantization property. Question: can we see that this phase is quantized? And what we can do, we can relate these phases to something that is known for systems with symmetry. So if a system has a symmetry, and we know that the n copies have SN symmetry, then we can associate this SPT index with the systems. Again, by kind of analyzing various automorphisms acting on my state and kind of producing new automorphisms, kind of undoing these transformations. So there is some natural way how to produce a 3K cycle out of a state with some internal symmetry SN. And the 3K cycle, you can express them, you express this K cycle in terms of this phase theta. In fact, in terms of nth power of this phase theta.
Why is it so complicated? So you can't show that the W0 and the W1 are order n.
W0,
The previous slide. W0 and W1, they're not. It's not obvious that those are order n.
Yeah, but we want a stronger quantization condition on this theta. So we will.
What's the strong?
Yeah, I'll mention it in a moment. So this is just a slide saying that we have some relation between this theta and this SPT index that takes values in third cohomology group of the symmetric group. But nice fact is that this cohomology is actually, it stabilizes after some n. And this cohomology group is equal to the Zmod 12 times 2 factor Zmod 2, and that gives this quantization condition for this theta, which is stronger. And this fact that this permutation symmetry acts non-trivially in holomorphic CFTs was noted by Theo, and it kind of expresses this anomaly for this SN symmetry in terms of the chiral central charge. But it fixes this chiral central charge mod 24. So, and that corresponds to the fact that this anomaly only knows about this nth power of this phase here. So if you want to kind of fix this chiral central charge as some real number, we have to consider, like, we need some finer invariant. And so the claim is that kind of reflection positivity provides. But CFT actually predicts a stronger quantization condition for this phase theta. So it predicts quantization condition that this power is equal to 1. And that corresponds to this quantization of chiral central charge in the units of 8. So at the moment, I don't know if how to kind of strengthen this condition. So in that kind of related to the fact that we don't know if there are like any invertible phases for which this kind of yet to be defined chiral central charge is like 2 or 4.
That's for boson.
Yeah, that's all for bosons. And maybe it's related to this question that you asked at the beginning. Okay, so now let me just mention how it works for fermions. Because for fermions, we actually have a concrete examples where we can compute things, and these are provided by these free fermionic models. And for fermions, but in general, for fermions, things are more complicated. Well, first of all, if you consider n copies of fermionic systems, then we have a bigger symmetry group. We not only have permutations, we also have fermionic parity for each copy. And this bigger symmetry group is hyperoctahedral group. What's interesting is this reflection positivity kind of interacts non-trivially with this fermionic parity. So somehow kind of relating spin and statistics. But if you consider free fermions, then this hyperoctahedral group is part of a bigger symmetry group, which is ON group. So for this kind of quasi-free state, this group, the symmetry group of n copies is actually enhanced to ON group. And kind of invariance associated with this ON group they correspond to Chern number that Alexei defined, and also like it was discussed in Mathias' talk. And for free fermions, we can compute this phase theta, and it coincides with this expression that we expect from conformal field theory. So basically, it allows us to prove that all these quasi-free states they actually represent non-trivial phases. So yeah, that's kind of a conclusion. My talk. So there is some hope that this kind of reflection positivity can provide us with invariance of the states. And allow us to prove some non-triviality in 2 dimensions. So I still don't know whether this reflection positivity holds in any dimension. So somehow one needs to prove this, that this canonical purification preserves locality. And I don't know how to prove it. But anyway, so like this is kind of maybe a way to produce invariance, but we still don't understand if these invariants are complete. I don't have any idea how to show completeness. Okay, I guess I'll stop here.